starting now. Yeah, the recording should be starting now. So, yeah, the key idea today is to see how we can improve the accuracy of machine learning models, and in particular, neural networks. So we'll basically be talking about the concept of bias versus variance. This is something we've touched before, so we'll go slightly deeper into that. And there are multiple things that we can do to improve the accuracy of the model. One of them is how the weights are initialized. So that's what we will look at today. And in the future.
Minimize screen?
Sorry?
Can you minimize the Skype screen, please? So we can see it. Thank you, Abhi.
Absolutely. So today's class will focus on how to initialize the original parameters, which will then be changed and updated by the optimization algorithm. And future classes, we'll look at other methods. So those are the two things we'll look at. One is understanding of bias versus variance. And secondly, how to initialize weights to have a good optimization. And I've shared with all of you a Colab. So Google Colab is essentially, it's like Python, Jupyter Notebook. And it has the basic libraries of deep learning available. And very importantly, it has access to GPUs. So most of deep learning requires a lot of processing power, and GPUs can do that in parallel. So they can be order of magnitude faster than CPU. It also gives you an option of TPU, but that requires some code change. GPU is sort of straightforward. So do you guys have access to this file, which is in Google Colab?
Checking.
Yeah. You just sent this, no?
Yeah, I sent the notebook about 2 hours ago.
Yep.
Dada, you have it? It's at shantanu.day42.
Yeah, I'm opening it. I still don't. I have it. I've received the mail. Yeah.
Okay, cool. So this should make a few things easier. I also found that Google has a course management system. So when necessary, we can use that also. So let's quickly talk about the training process. So generally, in standard machine learning, we'll have few thousand data points, and we break them into 3 groups. So one group is for training the model. Second is for validation. And third is for test. So essentially, we take a setting of parameters, or in case of neural networks, an architecture, and we train the algorithm on the data. Then we check it on the validation set, see if the performance is similar. then we can make a change again to the parameters and check again with the validation data. We do this a bunch of times. And when we've sort of figured out the hyperparameters, then we check the data, we check the predictions on the test set to see if the accuracy on training and the validation and the test set are more or less the same. That's the procedure. And in general machine learning, the way it's done is you will have a few thousand data points, and let's say 60% you keep for training, 20% you keep for validation, and for test you keep another 20%. Now, what's interesting is in deep learning, you normally have millions of data points. So if you're building a language model, people take entire Wikipedia and build it upon that. If you're building, let's say, a classifier on cats and dogs or some other kind of image, you can scrape the web and get millions of images. So deep learning tends to like more data. And in those cases, what seems to be the case is that you can give like 98% of the data for training because you have such a huge amount, and you can give 1% to validation and 1% to test. But even that 1% is of a million is a fairly big amount of data, and then you can look at the number and you can resample it and check the accuracy again, build some confidence intervals around it. But essentially, you can give most of the data, about 98, 99%, to training. And what's the other interesting thing is that suppose you have an application and that is generating a few thousand images. And you actually need many, many more for training. You need millions. So in traditional machine learning, the rule of the thumb was that all the three types of data should come from the same population. In deep learning, seems like you can get away with having similar distributions. So let's say you have certain kinds of images for your application. Let's say you're trying to figure out emotions, smiling versus frowning. Then you have those images of your customers. You have a few thousand. You can go online and scrape millions of smiling and frowning images. And that's slightly different distribution from your customers. but you might be able to get away with that. So you can train on the data that you've scraped from the web. But what is critical is that the data that you use for validation and the data that you use for test, those two should remain the same. So for training, you can get from another source, but when you validate the model, when you finally test the model, there the data should be of the population where you'd like to deploy the model. Does this part sound okay?
Abneet,
Mhm.
I have a more basic question.
Mhm.
In traditional modeling,
Mhm.
this concept of power and confidence, correct?
Mhm.
Which tell you based on the number of parameters you're estimating and the variability in the distribution,
Mhm.
what should be this minimum sample size required?
For hypothesis testing.
Yeah, so is there such a concept here? I mean, like, how do I know that based on the number of parameters I'm estimating in my deep learning model, I should at least feed it 6,000 images instead of 3,000 images? Is there any
Mm.
concept that defines what is the required sample size for deep learning model to be reasonably reliable?
That's a very good question. So in terms of models like regression, the rule of the thumb is that the number of rows of data should be 10 times the number of parameters. I haven't heard anyone mention the same for deep learning. So there essentially, in the absence of such a thumb rule, what we could do is take the images we have and build a reasonable model and see the accuracy. If we want to increase the accuracy and we want a model which is more powerful, and we make the model more powerful, then we can provide it more data and it will increase the accuracy. So I'm not aware of a good answer to that question, which would say a good relationship between the model size and the number of images. But in terms of actually playing with the model, you can definitely play it that way, where you start with what you have. And if you want to increase the accuracy, then either we can improve the quality of the data or the quantity of the data. That's generally what I see happening.
Yeah, the thing that I notice is that the model itself, as far as we are using, is a black box. It's some algorithm like your BGG or whatever.
Mhm.
So we don't really know the kind of functions this neural network generates. So it's such fitting of confidence to this depends on what is the scope of your neural network, and if that's to be used as a black box for the developer. It's either will comes prescribed like with the BGG, whatever that you use, the rule of thumb is this much. With the other program that you use, which has other neural network behind it, you should be doing that. So they should come prescribed. I don't think we can guess it without actually knowing the working of it. No?
Yeah, that's a good point. So VGG 16 had about 138 million parameters. I forget how many images were fed to it. I think there were a few 100,000. So if you're using something like transfer learning, where a model has proven itself on a certain data set, then the size of that data set gives a good hint of, if you want to retrain it from scratch, how much data might be required. So that's definitely one good place to start. Thanks for the questions and the answers. Okay, so this is a very interesting picture that shows the idea of bias versus variance. So let's say you're trying to hit a target. And in this case, the target is the red dot in the middle. So on the x-axis, on the left, we have low variance. On the right, we have high variance. And on the y-axis, lower is high bias and upper is low bias. So let's look at the case of bottom left, high bias and low variance. So the target is the red dot, but we are consistently missing the red dot. What's interesting is that all the points that we are getting to have a very low variance. That's the case of there's a consistent bias in the predictions, even though there's not a lot of variation in what's being predicted. If you look at the bottom right, that is a case where we have a high bias and we have a high variance. So we are consistently missing the target. And we are sort of varying quite a bit where we're heading. Now we look at the top right. Here the bias is low. So on average, we sort of get to the right spots. So if we take an average of all these points, we will get to the target. The problem is the variance. It varies a lot. And at the top left is the case where there's low bias. So we hit the target consistently. And the variance is very little. Sort of hitting at the target just about every time. So that is, so most of machine learning tends to revolve around these two ideas. You can have a model that overfits the data. So if you keep taking different samples from the population of your training data, the model that you'll get will be very different. So if you randomly take 10 samples, so let's say you have 1,000 data points, and you sample 100 randomly, you do this 10 times, and you build 10 models, and it may fit those 100 points perfectly, but these 10 models, their predictions on the 1,000 are all very different. So that's the case where your model is, its capacity is too high, it's too powerful. For the given data. So either you can increase the data for the model, or you can reduce the power of the model. Those are the general ideas. With the bias, the general case is that the model is not, it doesn't have enough capacity to fit the data correctly. So it always misses the target in a consistent way. So if you, in the case of variance, if you have a model that's too powerful, very high capacity, there's a term called VC dimensions that represents capacity. Then if you sample from a data of 1,000 data points, sample 100 points, you do that 10 times, and you get very different outcomes. If you average those, the average works out pretty good. Now, if you have a case of high bias, if you do the exact same procedure, you have 1,000 points, you take a sample of 100, randomly chosen, do that 10 times. The predictions will pretty much be the same. Their average won't be better than the individual predictions by much. So that's sort of the key thing that helps you figure out whether you have a problem with bias or you have a problem with variance. And this is a very crucial thing that Dr. Andrew mentioned in one of the first courses he gave. He said that he knows companies in Silicon Valley who spend 6 months trying to improve their model, but they try to do what was opposite of what they needed to do, and they are unable to achieve the right result. I have also seen things like this. So the first step to improve a model is to find out what's wrong. And one of the things to do is to figure out if this is a problem of high bias or this is a problem of high variance. And once you figure out, then let's say it's a problem of high variance, then as we just discussed, we can increase the data or we can reduce the capacity of the model, or in case of neural networks, try a different architecture. If you have a high bias, then we can increase the capacity of the model, or in some cases, try a different architecture for neural networks and see if that helps. Does that sound okay? We'll see more plots to make this idea clear, but does this chart in general make sense?
Yeah.
Yeah.
Awesome. Thank you.
So how does this apply to deep learning? It's mostly for modeling, no?
So deep learning also has the same issues.
But I thought deep learning is more like a discrete model, right? It just predicts certain categories. It doesn't give you a continuous variable.
It doesn't give what?
Like an output that is a continuous variable. It only says it's or a cat or a cycle or a road, but it will not tell you the speed is expected to be 27.5 kilometers per hour.
So that's a very good point. So most of the use cases that we see are of, like in images, are of classification, as you mentioned. In language also, we are trying to predict the next word. Or if we're trying to do like captioning, we take an image, we convert that, create a caption for that. Or we suggest emojis based on what's being written in the chat box. So as you said, those are all classification problems. Now, deep learning is also used for stock prediction, which is a problem of real numbers. And so the definition that Jeffrey Hinton is considered the godfather of deep learning. And he was one of the 3 who recently got the Turing Award for their contribution to deep learning. So his definition is a neural network that has more than one hidden layer is considered deep learning model for a deep neural network. So in that case, this would sort of apply. And in case of classification, it does apply in the sense of if we look at the accuracy on the training and the test data, and we see the accuracy is very high on the training data, but much worse on the test data. That would mean that the model was too powerful. It has overfit the data, and it had a high variance. So that's how this concept would sort of apply there. Does that answer your question?
But the variance would be hard to calculate. Anyway, we can talk about it later.
Yeah.
You need predicted versus actual, right? The difference between those two for variance calculations.
Right.
Here, more often, it's if in a classification, it's not easy to do that. If it's instead of a cat, you say it's a dog, you can't subtract the two and say this is the difference. It's either 100% or 0%.
Right.
But the model gives you a number, right? How accurately it thinks it's a cat.
Right. So on a given data set, you would get the accuracy numbers.
Okay, fine.
Okay. So this is the same idea explained in terms of a standard model. So on the left-hand side, we have a case of high bias. So we have a model which is theta 0, which is a constant, plus theta 1 into x. Let's say you're trying to predict the price of a house based on its size. The red points are the actual data points we're trying to fit, and the blue line is our linear model. So it'll always be off, and it doesn't have enough capacity to fit these data points. If we sort of resample the data and keep building linear models, they'll always have a certain amount of error from the actual data. And that error remain fairly constant and it won't decrease. On the extreme right, we have the same 5 data points. And now we have theta 0 to theta 4, and we have essentially a cubic term, x to the power 4, x to the power 3, and 2, and a linear term. So it is able to fit every data point but it doesn't really capture the real structure of the data. So if we keep resampling the data from this population, and we keep building the model with these features, it'll keep overfitting and it'll constantly be off from the target. And it'll constantly be off in different amounts. If you take an average of all of those, then you'll get something close to the target. If we take the middle one, that is sort of the right model. So it doesn't have too high a bias, too high a variance. Any question?
Okay, so I think my sense of variance is off here, Ravneet.
Mm-hmm.
The third model variance is exactly 0, correct? It is exactly lining up with the predicted ones.
It will have a high variance on test data. Sorry?
The error is 0.
Yeah.
The variance would be how much is it varying if we resample the data and we keep rebuilding the models. The prediction from those will keep varying, and as was that Vijayashree?
Divya.
As Divya mentioned, the error on the training set, that will be pretty high. Sorry, test set.
The validation, you mean?
Yeah, the validation.
So the variance really is applicable to the validation data set.
If we want to think in terms of error, yes. So when there's a case of high variance, then the error on the training set will be much lower than the error on the dev set. The validation set. And similarly, the error will be high on the test set.
Okay, so fine. Let's go on.
And the reason why it's sort of called variance is, right, if you resample the data from the population and you build different models, the predictions from all these models will have a very high level of variance. So let's say the size in this case varies from 500 feet to 10,000 feet. And you're getting a prediction for a house at 500 feet. And you have 1,000 houses. You randomly sample the data 10 times, each with 100 data points, and build 10 models. Those 10 models may have 0 error on the 100 points they were trained on. But let's say they didn't have a point related to 500 feet size. Those 10 models will have very different predictions for a house that has 500 square foot. Now, if you take the average, you might be sort of close to the real data. But individual models will have a very high variance in their predictions. Does that make sense?
I need to think about this more. So are we looking at one model or are we looking and comparing multiple models?
In this case, let's say we have these 4 features, x, x squared, x cubed, x4. The features are the same, but if you have 10 samples from the population, then the parameters that you'll end up optimizing for will be different. So the capacity of your model is same, meaning the features are same, but the actual hyperparameters may be different. The actual parameter values may be different. So in that sense, you can have 10 different models having 10 different sets of parameters, but they all have sort of the same architecture. They have the same capacity or power, you may say, in terms of how they can model the data.
Okay, let's continue, Avneet. I need to think a little more because I think I'm getting mixed up with my old ideas of this bias and variance.
Sounds good. This is the exact same thing. You can skip this. So this is sort of the idea that we were discussing initially. So if the model has very low capacity, let's say the case of it's just a linear model, while the model that's generating the real data is quadratic. So the capacity is low. So it'll have a high bias. As we keep increasing the capacity, the bias will keep decreasing. But if we increase the capacity too much, then the variance will increase. It'll overfit the data. And different models built from the same features or different samples from the population will produce very different predictions. The variance will be too high. And what we want to do is essentially find a balance. And that balance is essentially when the difference between the error on the training data and the error on the validation data is fairly little. It'll be there a little bit, but not too much. If they're very, very close, then it's more of a case of high bias. So we need to increase the model capacity. If the difference between the training error and the test error is too high, that would mean that we have too much capacity. The model is overfitting. So we need to give it more data, or we need to reduce the capacity of the model. And so this is essentially what a lot of time you'll be focusing on while building the model. And in some cases, many cases, the models will actually incorporate these ideas into the loss function. So we'll talk about that when we get there. So sometimes they incorporate these ideas into the algorithm. Other times we have to do it ourselves also.
So you just minimize the sum of the two.
Essentially, yeah.
Okay.
So, okay, the next thing that we'll talk about is sort of initializing the data, the parameters. So let's look at a single neuron. So in a neural network, we essentially have these three inputs coming in, x1, x2, x3. And we have these weights. So we take a dot product of the weights with the input and we sum them up. So x1 multiplied by w1 plus x2 multiplied by w2 plus x3 multiplied by w3. So that's the summation operator over wixi. And we have an activation function, and out of the activation function comes the output, the prediction. So this is more of just one neuron, more like a perceptron. And we have another term in here which was not above, which is this red arrow. So not only do we have the input multiplied by weights, we also have a bias term. So essentially W1 is multiplied by xi plus a bias term. So these weights and the bias term are the parameters that the model is trying to learn.
Is there one term or n terms, bias terms?
So in this particular case, it's n terms. It's actually n terms for the weights and one term for the bias. So in general, the main difference between standard machine learning and deep learning, this is what Chris Manning mentioned, and he's a Stanford professor known for his expertise on NLP. He said that standard machine learning wasn't much of AI. Essentially, we had a bunch of features, and then we did numerical optimization to provide weights to those features. And that's sort of what we're doing here. We are feeding features, those are our X values, and then we multiply those with weights, and the bias term is added. And the weights and the bias term is what we are trying to learn. In deep learning, the difference is that you don't have to provide the features. the model learns the features on its own. So that's the main difference between deep learning, why it's closer to AI as opposed to traditional machine learning. So an optimization algorithm will be needed to learn these weights and these biases. And essentially, what is the initial values that we assign to these weights and biases has a huge impact on how much time it takes to converge to the optimal values. And also, if we're having a certain amount of limited iterations, it'll end up deciding how well we converge, how accurate our model is. So that's one of the key points. The other thing is that we'll discuss later the idea of exploding and diminishing gradients. So when we have, those are some problems with deep neural networks. And to help with those also, it's very critical that the initialization is done in a thoughtful way. So that's what we focus on now. So what we have here, so I'd encourage you to go through these functions. I don't think we'll have time to go through it today. But essentially, these functions are all that you need to implement a neural network. So first, what we did was, we are just creating a data set. So this data set is created using scikit-learn, where it generates two circles of two different radius, and it adds some noise to them. So one class is red dots, the other class is blue dots. And what we are trying to do is find a classifier that separates the red dots from the blue dots. Does that sound okay?
Okay.
Okay. So essentially, we have our training data, which is train X, and our test data, which is test X. So these are nothing but the X and Y values. So essentially, these are the two dimensions of the plot. So each of those two values is one data point. We have train Y and test Y. And those are our labels of red and blue. So this is our function that takes the X and the Y value which uses this learning rate. And it has a certain number of iterations. We are picking 15,000. We are telling it to print the cost function. And this is the default, but we'll give it different values at different points in time. So the input data is just the two values for each data point, and then there's label. So let's look at different initialization techniques and how they impact. And if we have time, then we'll come back to looking at the code more closely. So one option is to initialize all the weights as zeros. So what do you think will happen if we initialize all the weights and biases as zeros? Let's run this and see what happens.
How is it increasing or decreasing? Which one is increasing? It's going to give you 0, correct?
Mm-hmm.
But which function is changing that weight a little bit for the next run?
So if the weights and biases are 0, then
Y will be 0, right?
Yeah.
Okay, run it.
So we ran this and there was no movement in the loss function. So there are sort of two issues. One is that everything ends up going to 0. The other thing is that all the neurons are essentially getting the same value. So because all of them are identical to each other, they're all not adding any extra value. Anytime we initialize the weights and biases to be exactly the same, and that is one of the big problems, that they'll all have sort of the same outputs, and there'll be no divergence between them. They all behave the same. So the other option is, and in this case, it basically predicted everything to be 0. So the accuracy was 0.5. It got half of them correct and half of them wrong. And this is just a plot showing that it gave the same prediction to all the data. If you look at the weights, they all remain. Sorry?
Where did the in your iteration, what is iterating through it? Where have we set up the iteration?
So
Okay, this is initialization, correct?
yeah, this is what the model is going to use for the initialization. The model is here.
Okay, I see. Where is it running through the iterations? So those are all initialization 1, 2, 3. It ran through 25,000 iterations or something like that, right?
Mm-hmm.
14,000 iterations. Where are we telling it to run through those number of iterations?
Here.
Mm-hmm. Okay. So initialization, we set it to 0, but through, are we, oh, I see, it's getting stuck, huh?
Mm-hmm.
Fine, okay.
Okay. So the other approach is essentially all the weights and the biases remain 0. Nothing changed. So the other approach is if we initialize them randomly. So this particular network that we've created has essentially 3 layers, and it's using for activation functions ReLU for the first 2 layers and sigmoid for the third. And I'll come back to the activation function in a few minutes. If I forget, please do remind me. So let's run this thing. Can you guys run it on your side also? Are you able to? So in this case, the parameters were initialized in a random way. And we see that the loss function started from here and went down to 0.38. This is, of course, an improvement. In terms of accuracy, on the training set, it's 0.83, and the test set is 0.86. So it's very close, which means the model is behaving well, and it's much better than the 50% accuracy we got earlier. So picking the random weights and biases sort of allowed all the neurons to learn different aspects of the problem. And they weren't duplicates of each other. And that helped. One of the things here is, let's look at the code for how this was initialized. So these are the 2 key lines. Where we use the random function and we multiplied those values by 10. So the initial weights were pretty high. And let's see what the parameter values actually ended up being. The parameter values are also somewhat high. So with random, we got to a decent amount, but the initial starting values were fairly high, and that can be a problem during the optimization, where sometimes there's an explosion and sometimes there's not enough gradient going back to the initial layers. We'll talk about those two in another class. But having the initial values too high can lead to some optimization issues, especially if many of the parameters end up being smaller values. So this one, these are the predictions showing ones and zeros. And this is just a grid map. So we create a grid, and at various intervals, we sort of get a prediction from the model. So this color of red and blue is what the model is predicting. And then the actual dots are the reds and blues. This is about 85% accurate. So definitely picking random numbers helped us to optimize much better.
Sorry, Avneet.
Yeah.
So when you generated this red and blues, this was just for creating your training data, or you generated this by plotting it along certain radii with some noise. So this is just your training data, right? If I understand it correctly.
Right. So,
and your actual aim is to say that whether your algorithm can tell around which radius my point will is. So when to call it red and when to call it blue should not depend on the noise with which you generated this training data.
Right. So when we generated the data, it essentially created two circles and added noise to them. Now, and the whole task is, can the model differentiate as to which circle the data came from?
But this very much depends on the noise with which you created your.
Yes, absolutely.
Yeah, okay.
So that is a very critical point. And theoretically, it's called the Bayes error. So what is the best error that you can achieve on a given data set? And figuring that out is very critical. because that's sort of the best that you can do. And for that, as you mentioned, the noise level is very crucial, because in this case, if we had more noise, then these two data points would be in each other's space more, and it would be very difficult to distinguish. In this particular case, we kept the noise level low enough, so with a good model, you can actually distinguish between both the labels, both the data sets coming from different circles. Does that answer your question, or did I miss something?
No, you already answered my question even before that. I just wanted to be sure this is what's happening when this is what we're doing.
Right. Yeah. So, yeah, this is a very interesting thing. So neural networks are, even a single layer is considered a universal function. It can learn pretty much anything, even something like this. Now you can just use the equation of a circle in a regression model and do that. For that, of course, you need the expertise and understanding of the data. A neural network can sort of figure out on its own something as difficult as a circle. So the third thing that we are going to do was, there was a paper in 2015 by Dr. He and his colleagues, and that essentially generates random data, but it scales it based on the number of layers. And that seems to work pretty well. Let's give this a try. So previously, our loss function was 0.38 around here. Now it's less than 0.1. The accuracy on training is 99%. On test, which is more reliable, as 96. That's fairly decent. This is what the precision boundary looks like, where it's trying to separate the red dots from the blue dots. It's a fairly decent job of that. So, in general, there are sort of two things that help a lot with optimizing a deep neural network. So one problem is that these numbers can start increasing a lot that are going through the network, and a range can become huge, and that becomes a problem with optimization. So and let me show you why. So if the numbers are huge, then you end up either getting a value of 0 and using a sigmoid function in activation, or a value of 1, the gradient becomes 0. So you can't really move much with a gradient of 0. The other activation function is tan h. Same story. So what is important is to sort of keep the values centered around 0. And so having an initialization with random numbers and sort of small random numbers centered around 0 is a good place to start. And the initial values are not too high. So the optimization can happen well. The gradients are reasonable. And for the very same reason, tan h is often used as an activation function in the middle layers because it sort of pushes everything between -1 and 1. So those are the sort of two key ideas for today. One of the toughest things with neural networks is sort of optimization. So CNN's convolution neural networks, the paper by Jan LeCun came out in '98. And most of the practical applications on images and deep learning come from CNNs. Most of the practical applications in language come from LSTMs, but that paper came in '97. So the actual popularity happened around 2012 when these data sets showed, these models showed a huge improvement in the accuracy because they're able to find ways and hacks to actually optimize these models. Optimization is sort of the big issue with neural networks. It gets even more complicated when you're dealing with reinforcement learning, which is used in places like robotics. So this is one of the things that will help you. If you see, let's say, a lot of NANs, then most likely your weights are exploding. So one of the fixes for that is to ensure that the initialization has small values centered around 0 and maybe has some tan h functions, activation functions to again center it back if they have exploded too much. So this is one of the tricks in your basket. The other thing that we discussed is the bias and variance. So in traditional machine learning, if you improved one, you would have to give up on the other. There was a trade-off. In deep machine learning, you don't have that trade-off as strictly as traditional machine learning. You can actually just improve on your variance or just improve on your bias without impacting the other too much. And so that is sort of the fundamental idea, is to look at the error on your training data, look at your error on the test data. If there's a huge gap, then you probably have a high variance. If there's nearly no gap, then you might have more of a bias issue. You have a high variance, you can solve it by giving it more data, or reducing the capacity of the model. And if it has high bias, then you can increase the capacity of the model and improve the prediction. So those were the two ideas. There's a lot of code in here, and pretty much this code builds the entire neural network, does the entire optimization. I would encourage you to play with it. You can go to the initialization and make some changes to that. So in the second case, we'd multiply it by 10. You can increase that, decrease that, see how it optimizes, and play with those kind of things. Instead of initializing with zeros, you can initialize it with, let's say, 1s or 0.5 or something like that. So you can play with that to get a sense of how the initialization impacts. And you can sort of read the entire code and get a sense of how a neural network is built and optimized. So that should be a fun homework for you. That's all that we had planned for today. Do we have any questions?
Where is the file you uploaded for the this one?
Say that again, please.
You have a command to upload files, right, at the beginning?
Right, those were image files.
Where is that? Is that on Google or?
So this file, like this image, I uploaded it from my desktop. I got it from Google, put it on my desktop, then uploaded it to the Colab.
Okay.
Do you see it in your Colab file?
No, I don't see it.
Okay, I didn't realize that. So I'll have to figure out how to have it such that you can see the image files also. So I'll dig into that. Thanks for sharing that point. Okay, guys.
Actually,
Yeah, please go ahead.
I think there is one image. Anyway, I think it's fine. That's all I had. I'll just check it out. Don't worry.
Okay, sounds good.
There is one image that is there. That's a PNG file.
Interesting.
No. Actually, both are there. Sorry, I might have done something here. I have two PNG files.
Okay, so maybe I saved it when I had only few, and I shared that. I just saved it again.
Fine.
Maybe now it has more.
Okay. So it is. Am I working on the version that you're running? Is it one version that we are all sharing?
Yes.
That's a good question. I am not sure.
So it said it's going to reset a lot of things when I ran. Fine. So it is one file that all of us are sharing, is it?
Yeah, you have to start running it from the start.
So what's the end URL that you have, the last 4 characters? I have KPFP.
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 No, I don't see that. Maybe it's a copy of the version here. So this is my URL. Fine. It's a different URL.
Yeah, it's a different URL.
You have the
I hope.
same data, but you'll have a different playground created for you.
Nice.
It opens in edit mode, which means that I'm looking at your version, and then if I say go to playground, it creates a new version or a copy of it.
Yeah, it copies the code over and gives you your own environment to run.
But if I save it, it goes and writes to the original one. No? We have to check that, right?
That time check, but gives you a one saved one.
Would you like to try that? If you just enter something, see if that changes for the rest of us.
So I have 3 saves in the drive, a copy as a GitHub disk or a save a copy in GitHub. Okay, how do you access what I've saved?
I just refreshed mine. If what you have saved
Somebody is
changed for all of us. So what is it that you changed?
I just did a print at the very first line.
Yeah, I don't see that. So it seems like you have your own copy, which is pretty cool.
Okay. Let me save it again. Where have you saved it? In GitHub or on the in the drive?
It's just saved in Colab right now, under my drive.
Okay.
This is just like any Google document.
Yeah, it's just creating copies and copies of it. That's all. So it's not a shared environment, it looks like. Fine. Okay. Thanks, Abhi.
And it has this cool thing where if you go to settings, you can pick GPU.
Okay.
Okay. Cool, guys. Have a wonderful weekend.
Thank you.
Take care.
Yeah, bye.
Can you stay 2 minutes later?
Yes, I'll just stop the recording.